Alright, so we're going to look at this thing called the Nth Roots of Unity, which are basically the solutions to the unit equation. So z to the power of n equals 1 or minus 1. So we call these the nth roots of unity. If you were to plot all the solutions, we'll end up with a lovely regular polygon, if we were to join them up, with the vertices all on the unit circle. Because remember how we said all the solutions are going to be symmetric? So you'd end up with a nice polygon. Let's have a look at z to the power of 5 equals 1. So if we use the marks for it, of course 1 is a real number, so all the coefficients are real. So I know they're going to appear in conjugate pairs, so I'll go with 0 plus or minus 1 plus or minus 2 as my solutions, and I'll end up with cis 0, cis plus or minus 2 pi and 5 plus or minus 4 pi and 5. So if I was to do it via the diagram, well, I know obviously 1 is a solution to z to the power of 5 equals 1. So there's my first solution. I know they're going to be evenly spaced. So if I divide 2 pi by 5, strange how I get 2 pi and 5. So I know my next solution's up there at cis 2 pi and 5. The conjugate must be there, cis minus 2 pi and 5. Go around another 2 pi and 5, there's cis 4 pi and 5, and its conjugate must be there. And so as I say, if you were to join those up, you'll end up in this case with a regular pentagon. And they're all sitting on the unit circle. Here's a standard sort of question. So if omega is one of the complex roots of z to the power of 5 minus 1 equals 0, show that omega squared, omega cubed, omega to the power of 4, and omega to the power of 5 will be the other solutions. Now, when they say a complex root, they're meaning a non-real root. Okay? So something that has an imaginary power. Therefore, 1 is not the complex root. 1 would be the real root. So how do I then prove the other ones are roots as well? Well, z to the power of 5 is equal to 1. We know that. And they've told us omega is a solution. So therefore, omega to the power of 5 must be equal to 1. I'm going to play around with the indices a bit here. So if omega to the power of 5 is equal to 1, then omega to the power of 5 to the power of 5 must equal 1 to the power of 5, which is 1. So omega to the power of 5 is also a solution. Now, omega squared to the power of 5, I could rewrite as omega to the power of 5 squared. And we know omega to the power of 5 is equal to 1. And 1 squared is 1, so therefore omega squared is a solution. Omega cubed to the power of 5, I could rewrite as omega to the power of 5 cubed. And we know omega to the power of 5 is 1, and 1 cubed is 1. So omega cubed is a solution. Omega to the power of 4 to the power of 5 is equal to omega to the power of 5 to the power of 4. And we know omega to the power of 5 is 1, and 1 to the power of 4 is 1, so omega to the power of 4 is a solution. So if omega is a solution, or is a root, then so is omega squared, omega cubed, omega to the power of 4, and omega to the power of 5 as well. Now, let's start off the same. Well, z to the power of 5 is equal to 1. Then we know, yes, omega to the power of 5 is equal to 1. But here's where it differs a little bit. I'm simply saying, well, hang on. If k is an integer, then omega to the power of k to the power of 5 will always equal omega to the power of 5 to the power of k. That will always be true, so long as k is an integer. Well, that would be 1 to the power of k, and 1 to the power of k is always 1. So there's a much quicker way of saying, well, hang on, that means if omega is a root, then omega to the power of k will always be a root as well, where k is an integer. Now, it could be negative as well. I mean, we've just shown that squared, cubed, power of 4, power of 5 are solutions. But in fact, omega to the power of 6 would be a solution. Omega to the power of 7, 8, 9, 10 would be a solution. Omega to the power of minus 1 would be a solution. Minus 2, minus 3, minus 4. They would be solutions as well. Some of them would be the same solution as others, but to the power of any integer will be a solution. Another question they love. All right, we've now determined that if omega is a solution, then omega to the power of anything, as long as it's an integer, is a solution. So 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0 is what we have to prove. I just said the 5 roots of our equation was omega squared, etc., etc., etc. So the sum of the roots would be minus b on a. And if you have a look at our equation, well, b would be the coefficient of z to the power of 4. Which in this case, there is no power of z to the power of 4. So sum of the roots would be 0. And the other thing I've done is I've said, well, I know that omega to the power of 5 is equal to 1. So I just put that in and I've got 1 plus omega squared and so on. There's my result. That's one way you can do it. Another way you can do it, okay, so it's omega to the power of 5 minus 1 is equal to 0. I could factorise that. And so we get omega minus 1. And then you'll remember in the second parentheses, we get all of the powers until we get down to 1. So it'll be omega power 4 plus 3 plus 2 plus power 1 plus 1 is equal to 0. Well, that comes from this relationship. Remember, we looked at difference of two squares, we looked at difference of two cubes. But that, remember, generalises out to the power of anything. So I'm specifically looking at omega to the power of n minus 1 will always factorise to be omega minus 1, and then 1 plus omega squared, and so on and so on and so on, up to n minus 1. Well, that means 1 plus omega squared plus omega cubed plus omega power 4 must equal 0. Because 1 minus omega can't equal 0. Because remember, omega was a complex root. So omega can't equal 1. Which would be a real root. So it must be the other factor that's equal to 0. That's one way we could do it. And yet, another way we could do it. Let's have a look at this thing. 1 plus omega squared and so on. What we've got there is a geometric series. First term is 1. The ratio is omega. And we have 5 terms. So if I sub that into our formula, we get 1 outside of omega to the power of 5 minus 1 over omega minus 1. But, oh, hang on a sec. The equation we're solving is omega to the power of 5 minus 1 is equal to 0. And so that must equal 0. So there's several ways we could do that question. Now, if we had to find the quadratic equation then, and we know the roots of this new equation are going to be omega plus omega to the power of 4, and the other root's going to be omega squared plus omega cubed. But we can create quadratics by playing around. Well, what's the sum of the root? The sum of the roots would end up being omega plus omega to the power of 4 plus omega squared plus omega cubed. But we now know that's going to be negative 1. Because 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. So if I move the 1 to the other side, I get omega plus omega 4 plus omega squared plus omega cubed is negative 1. So I know the sum of the roots of these is equal to minus 1. Product of the roots. What happens when we multiply these two things together? If I expand that whole thing out, I get omega cubed plus omega 4 plus omega 6 plus omega 7. I'm going to simplify that a little bit, because remember, we know omega to the power of 5 is equal to 1. So therefore, omega to the power of 6 is the same as omega. And omega to the power of 7 is the same as omega squared. And look what we got. There it is again. Omega cubed plus omega 4 plus omega squared. Well, that's equal to negative 1. Our quadratic is therefore x squared plus x minus 1 equals 0, minus the sum of the roots, x plus the product of the roots. So this time we're playing with the cube roots of unity. So omega is a complex cube root of unity. They've told us we don't have to go and prove it. They've given the fact. So 1 plus omega squared is equal to 0 for our cube root of unity. Evaluate 1 plus omega squared cubed. Now, I could expand the whole thing out, but I'm not going to. Because, you see, if I know 1 plus omega squared is equal to 0, then 1 plus omega squared is negative omega. And now I'm cubing one term instead of cubing two terms and having to come up with a huge expansion. Minus omega cubed would be minus omega cubed. And we know omega cubed is 1. Therefore, my answer is negative 1. What about if I had to work out this algebraic fraction? So we'd get a common denominator and play around with that. But hang on, before I do that, those denominators I can rewrite. Because 1 plus omega would be the same as minus omega squared. And then in the second fraction, the denominator, 1 plus omega squared is the same as minus omega. It's still an algebraic fraction, but now it's a little bit easier. The common denominator is omega squared, and on the top I'll get minus 1 minus omega. Hang on a sec. Minus 1 minus omega, well, that's omega squared. Going back to our original equation again. So we've got omega squared and omega squared, which is 1. Now it's not a huge surprise a lot of these answers are turning out to be 1 and minus 1, because we're playing with roots of unity. So now we're going to create a cubic equation, and now cubic is going to have roots 1, 1 plus omega, and 1 plus omega squared. Well, I know z minus 1 is a factor straight away, because they've told me a real factor. That means the second factor is a quadratic, which will be z squared minus the sum of the roots. Well, if I add the other two roots together, I'll get 2 plus omega squared, plus the product of the roots. If I was to multiply those together, I'll get 1 plus omega squared plus omega cubed. But that will tidy up because we know 1 plus omega squared is equal to 0. So 2 plus omega squared is 1. And 1 plus omega squared plus omega cubed will be omega cubed, which is 1. So we end up with z minus 1, z squared minus z plus 1 is equal to 0. So there's our equation. If we expand it out, it ends up looking like that. Z cubed minus z squared plus z minus z squared plus z minus 1. What's that? There it is. Z cubed minus 2z squared plus 2z minus 1 is equal to 0. So what about if we had to solve an equation like this? It's a pentic equation. How do we factorise it? Well, the trick is I'm not going to. I'm just going to change the equation. Because I know z to the power of 6 minus 1 would be z minus 1 times that expression. So, and I know the solutions to z to the power of 6 minus 1. They're the 6th roots of unity. So 2 pi k on 6, k will be 0, plus or minus 1, plus or minus 2, and 3 as well. So if I now want to solve this equation, instead of solving that one, I'm going to solve this one, where I'll multiply the top and bottom of the fraction by z minus 1. Because the top of the fraction is z to the power of 6 minus 1 equals 0. And if I want to solve a fraction equaling 0, it must be the top of the fraction that equals 0. But for this one, the bottom of the fraction can't equal 0. So I know I want the 6 roots of unity, but not the solution z equals 1, because that would give me 0 on the bottom of this new fraction I've created. I want the other 5 solutions. So therefore, there are my solutions. Cis pi and 3, cis minus pi and 3, 2 pi and 3, minus 2 pi and 3, and cis pi. And we can tidy those up if we want to, because they're all exact values. And that's what we end up with, a half plus root 3 on 2i, and so on and so on and so on. So we get the 5 solutions. Here's quite an old HSC question. This time we were dealing with the 9 roots of unity. So z to the power of 9 minus 1 equals 0. And they actually told us which solution. So it's a complex solution, but they've made it the very first one. So cos 2 pi on 9 plus I sine 2 pi on 9. And they want us to show that omega to the power of k is a solution. So this time we have a very specific solution. W to the power of k, using de Moivre's theorem, would be cis 2 pi k on 9. And k will equal 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have cis 2 pi on 9 to the power of k, which is the one they told me is omega. And look what we got. It's z equals omega to the power of k, where k is 0, 1, 2, 3, 4, 5, 7, 8. In other words, where k is an integer. Prove that. Rather long expression. But all it is that standard question again of 1 plus omega squared, and so on and so on and so on, is equal to 0. So which way did I choose out of those 3 methods? I went sum of the roots. Those are low. Sum of the roots is 0. So I know that that must be true. And then move the 1 over, and we get the result they're looking for. Cos pi on 9, cos 2 pi on 9 times cos 4 pi on 9. Well, if I was to factorise z to the power of 9 minus 1, then that is what I would get. It's z minus all of the roots, each factor. But you'll notice I've written them rather strange. Instead of just going power 1, 2, 3, 4, I've deliberately grouped them. And the way I've deliberately grouped them is putting conjugates together. How do you know they're conjugates? The 2 powers add up to give 9. So if the 2 powers add together to give whatever the nth root of unity is, so it adds up to give n, you know they're conjugates. So that means when I expand out by z minus w to the 8, I'm saying it's z minus w times z minus the conjugate of w. That will become minus twice the real part, which is cos 2 pi on 9, z plus the product of the roots, and the product of the roots would end up being 1, because the real part squared plus the imaginary part squared is 1, because we're dealing with roots of unity. They all lie on the unit circle, so x squared plus y squared will always be 1. The next one will be minus 2 cos 4 pi on 9, then 6 pi on 9, then 8 pi on 9. How am I going to just get a product of 3 things? I'm just going to tidy that up a little bit. Whoa, what did he do? You'll notice this factor, z squared minus 2 cos 6 pi on 9 z plus 1, looks like it's disappeared and been replaced. So 6 pi on 9 is the same as 2 pi on 3. It's an exact value. Cos of 2 pi on 3, negative a half, but times the negative 2, we get plus 1. What's the next thing I'm going to do? I want to somehow turn this into a product. Oh man, well I've sort of got a product, but if only there was a way of getting rid of this z squared plus 1 in each of these parentheses. And then I'd have the cos times cos times cos. How could I get rid of z squared plus 1? In other words, how could I make z squared plus 1 equal to 0? Let z equal I. Because then you'll have I squared plus 1, and I squared's negative 1. Negative 1 plus 1, 0. So if I sub that in, the left-hand side becomes I to the power of 9 minus 1, and we're left with I minus 1, minus 2 cos 2 pi on 9i, minus 2 cos 4 pi on 9i. The z squared plus z plus 1 just becomes I. And then our last one is minus 2 cos 8 pi on 9i. Well, I to the power of 9. What's I to the power of 9? I. So the left-hand side is I minus 1, which will divide with the I minus 1. In all of those, I've got a factor of I, a factor of I, a factor of I, and a factor of I. So I've got I to the power of 4. I've also pulled out the negatives. Negative times negative times negative is negative. I'm starting to get there. 2 times 2 times 2. 8. Wasn't a trick question. The I minus 1 cancelled with the I minus 1. Divided both sides by negative 1. The I to the power of 4 is 1. So I now have 8 cos 2 pi on 9, cos 4 pi on 9, cos 8 pi on 9 is negative 1. What were we trying to prove? Wasn't that, was it? It was, but hang on a sec. Cos of 8 pi on 9, I could rewrite as minus cos pi on 9. We're in the second quadrant, cos is negative. Acute angle would be pi on 9, giving me cos pi on 9, cos 2 pi on 9, cos 4 pi on 9 is equal to 1/8. All right, so 3C is playing with these wonderful roots of unity.